Scientists invented concrete that repairs its own cracks over a decade ago. It works. The research is rock solid, and almost nobody is using it. That is not a mystery. That is a story about how engineering actually works. Because the problem this material is trying to solve is enormous. Every concrete structure on the planet is cracking right now. Roads, bridges, tunnels, dams. Concrete is strong under compression, but weak under tension. The moment it carries load, shifts thermally, or the ground beneath it moves even slightly, hairline cracks begin to form. Those cracks are invisible at first, but they are open doors. Water gets in, then chlorides, then sulfates. They reach the steel reinforcement inside. The steel corrodes and expands. The concrete spalls from within. The structure weakens long before its surface shows any warning.
The United States alone spends over $20 billion every year just maintaining its concrete infrastructure. Globally, the number runs into the hundreds of billions, and almost all of that money is being spent reacting to damage that, in theory, a living material could have prevented by itself. So what is self-healing concrete? How does it work? And why, if it genuinely works, is it still not being poured into every bridge deck and tunnel lining on the planet? Here is where it gets interesting. Because the answer is not about the science. The science is already solved. The answer is about something far more uncomfortable. Money. And who pays it and when.
The most studied version of self-healing concrete uses a bacterium called Bacillus subtilis. This species has one extraordinary property. It can form spores. A spore is a biological dormancy capsule the bacteria retreat into when conditions become hostile. Bacillus subtilis spores can survive inside the alkaline, oxygen-free environment of a concrete matrix for decades. They wait, inactive, patient, invisible. When a crack forms and water seeps in, conditions change. The spores activate. The bacteria emerge and begin consuming a nutrient source, typically calcium lactate, packed alongside them into the mix. As they metabolize these nutrients, they excrete calcium carbonate. That mineral crystallizes inside the crack, physically filling it, sealing it, and restoring the concrete's structural integrity. With no human intervention, no machinery, no maintenance crew. In laboratory tests, Bacillus subtilis sealed cracks completely within 21 days. A 2025 study in Scientific Reports confirmed this under controlled curing conditions. A separate study in the Journal of Materials Science found bacterial concrete showed a 25 to 40% increase in compressive strength compared to conventional concrete of the same grade. The bacteria were not just healing damage, they were making the material stronger.
So the science works. The bacteria work. The strength numbers are better. But here is the problem that nobody talks about in the headline articles. Bacterial concrete costs roughly 2 to 3 times more per cubic metre than conventional concrete. And in infrastructure procurement, which is almost entirely publicly funded and almost entirely cost-driven, that number ends the conversation before it starts. Think about how a major infrastructure project gets built. A government department sets a budget. Engineers design to that budget. Contractors bid on the lowest viable cost per unit. The entity that approves the pour is not the entity that will pay for repairs 20 years later. A different budget cycle, a different minister, a different administration. The upfront cost is visible today. The repair saving is invisible. It belongs to a future that nobody at this table is responsible for.
But here is where the argument flips, because comparing the cost of bacterial concrete to conventional concrete is the wrong comparison to make. The right comparison is life cycle cost, total cost of ownership over the full service life of the structure. And when that calculation is done, the numbers look very different. A 2025 study in the Journal of Materials Science estimated that bacterial concrete can extend structural service life by 30% or more. If a bridge normally requires major rehabilitation every 20 years, a 30% extension means 6 additional years of service before intervention, potentially tens of millions of dollars saved in repair contracts, lane closures, equipment mobilization, and traffic management. The upfront premium pays for itself many times over, but only if the same organization that builds the structure also pays to maintain it, and that is rarely how public procurement works. Now, here is the second problem, and this one is purely technical. Bacterial effectiveness does not last forever inside the concrete.
The healing mechanism depends on spores remaining viable across the full life of the structure, potentially 50 to 100 years. In laboratory conditions, viability over decades has been demonstrated, but real structures face temperature swings, freeze-thaw cycling, chemical contamination, and sustained dynamic loading that laboratory specimens never experience. A 2024 review in Science of the Total Environment found that healing efficiency diminishes over time as nutrient supplies are consumed and bacterial populations decline. A crack that forms in year 30 may encounter far fewer active bacteria than a crack that forms in year 1.
But engineers are already solving this, and the solution is elegant. Rather than mixing bacteria freely into the concrete, researchers are now encapsulating them, sealing the bacteria and their nutrients inside tiny protective capsules made of clay, silica, or polymer before adding them to the mix. The capsule shields the bacteria from the alkaline environment and only ruptures when a crack physically breaks through it. The crack itself triggers the repair. Bacterial survival rates have improved dramatically. The active healing window is extended.
And there is a parallel track developing that sidesteps living organisms entirely. Chemical self-healing systems use capsules filled with epoxy resin or sodium silicate instead of bacteria. When a crack ruptures a capsule, chemistry flows out, fills the fracture, and hardens. No biology, no viability window, no nutrient depletion. Stable for the full structural life. Cheaper to produce, easier to quality control at industrial scale. So right now, two approaches are competing for the same problem. Biological systems, more elegant, potentially more powerful, longer healing window with encapsulation, and chemical systems, more immediately practical, more cost-stable, already entering mainstream use. Neither has won, and depending on the application, neither should.
For high-value, difficult-to-access environments, tunnels, marine foundations, underground water infrastructure, nuclear containment, the bacterial approach is already making real commercial inroads. A Dutch company called Basilisk has been producing bacterial concrete commercially for over a decade. Their products have been used in documented infrastructure projects across Europe. In those environments, the cost premium is trivially justified by the cost of manual crack repair in a location no human can easily reach. And a 2025 review in Frontiers in Microbiology pointed to something that could change the calculation entirely. A hybrid biological system combining bacteria with fungi. Fungal hyphae physically bridge crack faces, while bacteria deposit calcium carbonate within them. Mechanical bridging plus chemical sealing in a single living system. The researchers called it a more robust healing network than either organism alone. It has not left the laboratory yet, but it is coming.
Here is what that means at the scale of civilization. Every bridge, every tunnel, every dam ever built has one thing in common. It cannot respond to damage. It endures passively until it cannot. And then humans intervene, expensively, reactively, and always too late to prevent the damage that made the intervention necessary. The concrete holding up the bridge you drive across today will crack. It is cracking right now in ways no instrument is measuring and no engineer is watching. Water will find those cracks. Steel will corrode. And eventually a maintenance crew will arrive with equipment to fix what a handful of dormant bacteria, waiting in the right mix at the right cost in the right structure, could have handled on their own. The science is ready, the economics are moving, and the only thing standing between the bridge and the bacteria is the procurement system deciding who pays for it. Thanks for watching. Like and subscribe for more civil engineering explained simply.